equivalently, we also confirm that there is the differences between the means of different groups or not. But we can see that in case we reach just as 0, we just know that there's some treatment or factor level means are different. We just know that there's something different between the means of different groups. But which one are different? We don't know, right? So in example 1, we are considering the questions about the comparison between the threshold means of different level of Howard concentration. At the end, we already confirmed that really there is differences between the average tensile strength of different levels of Howard concentration. But we don't know which levels create the differences. Level 5 to 5% to 10%, or the difference between 10% to 20%, or 20% different to 25%. Which one different to each other? We really don't know. Okay. So let's listen to the questions. We need the method after Anova. In case that we reach just as 0, we want to know which pair of treatment means will be different to each other. Okay, and that is the method called the multiple comparisons. Okay, the multiple comparisons, because we compare each pair of the treatment means mu1, mu2, mu1, mu3, mu1, mu4, mu2 and mu3, mu2 and mu4, and mu3 and mu4 for every pair of the means after Anova. And remember that we only do the multiple comparison methods in case that we reject the null hypothesis as 0 in the Anova model. That's the reason why we call this is the method following Anova. Only the case we reject as 0. Okay. And now there's several methods to do the multiple comparisons after Anova. But the easiest one I will introduce to you is the Fisher's least significant difference method. And for the short term, which we call the LSD method. Okay, and later we will see what is the LSD method, why we call the LSD method. Okay, so anyway, in summary, the Fisher LSD method tries to compare all of pairs of the means with the hypothesis as 0 will be mu I equals to mu j, and alternatively mu I different to mu j. Okay, this is our target. So if you have 4 groups, so totally we have 6 hypotheses. Okay, we need to make the hypothesis for every pair of mu I and mu j. This is the target. Okay, because we want to explore which term, which means will be different to each other. Okay, to do it, return to the board. We need something. Okay, I let you few seconds to recover your knowledge about chapter 6. Why? Can you recognize that? Now the target is we want to make the hypothesis about mu I equals to mu j, or mu I different to mu j, where I indicates group I, j indicates group j, and where we have the assumption that the populations yi independent with the sample yj. It means that observations belong to different treatments will be independent. Moreover, yi and yj, any observation belong to different treatments are assumed to be normal distribution, with the mean is mu I, and the variance is sigma square. And yj also follow normal distribution, mu j and sigma square. So can you recognize? It's similar to the idea of comparing 2 means, because here it's reduced to the question about comparing 2 means. Right? It's just comparing 2 means under the assumption that the populations follow normal distributions and 2 populations are independent. Right? So, according to chapter 6, what should we do? Always, when we when we working with the hypothesis test for the mean. Firstly, we identify a point estimator. That is estimate, or that's we estimate for the parameter we're using, right? So we have two parameters, mu I and mu j. Estimate for mu I, of course, we use the sample average yi bar. Okay, so we have yi bar is the estimate of mu I. Yi bar follow normal distribution. We did it many times. Distribution of the sample average always follow normal distributions if the sample follow normal distributions. Okay, the mean equals to mu I. The variances equals to sigma square over the sample size. Because here the sample size is n, so we have sigma square over n. Okay. Then similarly, y bar also follow normal distributions with the mean equals to mu j, and the variance equals to sigma square over n too. Okay. So the target is make the comparison between mu I and mu j. So we consider the estimate of mu I minus mu j will be consider yi bar minus yj bar. Okay, it's follow normal distribution with the mean is maybe I should write down. So we consider yi bar minus yj bar as the estimate of is an estimator of mu I minus mu j, right? Then we know that yi bar minus yj bar also follow normal distribution with the mean is mu I minus mu j. Sigma square, the sum of two variances, we have 2 sigma square over n. You must able to do it, right? So we already know the estimator. The second step, we need to know the HE, right? HE, I told you many times, SE of the estimator always equals to the square root of the variances of the estimator, or SE the estimated of the variances of the estimator in case that the variances is unknown. In this case, because sigma square is unknown, so of course we need to estimate it. Okay, so we have HE of yi minus yj bar is the estimated, which is 2. Sigma square is estimated by sigma square half over n. We take the square root. Where what is sigma half square? Sigma half square is, in this case, rolled down. We already rolled down here. MHE is always an unbiased estimator of sigma square. And I told you that it means that in the Anova model, we always able to choose MSE to estimate for sigma square. It means that sigma square hat equals to MSE. That's all. Okay. So we write sigma square equals to MSE. Okay. Means that SE equals to square root of 2 sigma square hat will be MSE over n. Okay. So almost done. The first step, identify the estimator. Second step, identify HE. So we derive to the test statistic. the test statistic is T0. I know that is T0 because the test with the normal assumptions and sigma square is unknown. So surely we use t-test. Okay. So T0 always equals to the estimator. Estimator, in this case you have yi bar minus yj bar. Minus the constant. The constant we are considering is 0. Because we consider mu I minus mu j equals to 0. Or mu I minus mu j different to 0. Okay. So this is 0 over HE, where HE you already found here. Because it follows student distribution. With degree of freedom in student distribution always equals to degree of freedom on the way we calculate for sigma square half. Because sigma square half equals to MHE equals to HHE over Kn minus 2, Kn minus 1. So degree of freedom in student distribution is exactly equals to the denominator here. So Kn minus 1. Okay, so we have that. So it means that we have the t-test. And we know that the t-test in case of two-sided. So we readjust as 0 if and only if the absolute value of T0 greater than the critical value, which is T Kn minus 1 alpha with 2, using alpha with 2 because we have two-sided. If we have one-sided, so using alpha, that's it. It just return to the question about the t-test. It's totally the same as we have done in chapter 6. It's just different by the way we calculate for sigma square using MHE. Right? Agree? I want that you could recognize this is still a question about the t-test. So you should be familiar with the knowledge we have done in chapter 6. It's just different in t-test here that we use MHE to estimate for sigma square. That's all. Okay? One small step. Of course, using the t-test here, you're already able to answer for the question whether we should readjust at 0 or not. But remember that we need to repeat the t-test many times because we need to compare for every pair of the means. So if we have k equals to 4, we repeat the t-test 6 times. It's really not convenient. Okay? So just for convenience, starting from the t-test. Okay? I rewrite the condition to be to readjust at 0 here. Equation star. In equation star. Equivalent that because T0 equals to, I let this absolute value of yi bar minus yj bar over HE. Okay? Greater than T alpha over 2 Kn minus 1. So equivalent to, because HE always greater than 0, so I write absolute value of yi bar minus yj bar greater than HE multiply T alpha over 2 Kn minus 1. Okay, where HE we already found. Where HE, so this term equals to square root of 2mSE over n multiply T Kn minus 1 over 2 alpha over 2. So the left term we denote it by LSD. This is LSD. This is called LSD. Okay. So what does it mean? We can recognize that LHD actually is just the constant, because HE you calculated from the data. Tk minus 1 alpha over 2 is the critical value of student distribution. We found it from the table. So LHD is just the constant. So you can calculate it only one time. And then to make the conclusion whether we should readjust as 0 or not, we're just basing on the differences between two sample average. And the differences between two sample average will be very easy to calculate it. Okay? So that's the reason why we have the LHD method. The LHD method. The LHD method is just the other way to write. It's just the way we rewrite the t-test, nothing else. The LHD method is still be the t-test. Once we rewrite it in the second way. Now, for any test, for any pair of the means, we only need to calculate the absolute value of two differences in the sample average. And if we see that this the distance between two sample average is greater than LHD, we confirm that we readjust as 0. If it's less than LHD, we confirm that we don't have enough evidence to readjust as 0. Okay, it's very convenient. And that's also the reason why we call this term is LHD. L means least. LHD means the least significant differences. Least significant differences, it means that the smallest constant that allow us to readjust as 0. This is the smallest one allow us to readjust as 0. To know whether there is the differences between two population means mu I and mu j, we focus on the differences on two sample average. If the given two sample average will be at least greater than LHD, LHD is at least the smallest accepted distance between them, we readjust as 0. If it's less than this smallest acceptance, we said that we won't readjust as 0. Okay, that's the reason why we have the name LHD. Okay, that's all. Okay, now return to the slides. I make the summary on the slide. So, basing on the Anova assumptions, the test statistic value T will be yi bar minus yj bar over he will be square root of 2 mhe over n. This is the t-test. Rewrite this in terms of LHD. We have LHD equals to the critical value multiply he. Okay. We readjust as 0 if the distances between them greater than LHD. Otherwise, we won't readjust as 0. Okay. And of course, we also get the confidence interval from mu I minus mu j. Very easy. Okay. Because the confidence interval for any parameter always written between the estimator plus or minus the critical value multiply SD. So all of this term will be LHD. That's all. Okay. So it means that on the way we construct the hypothesis test using LHD, we also able to write out mu I minus mu j also between yi bar minus yj bar minus LHD and yi bar minus yj bar plus LHD. Very convenient. See? We just need to calculate LHD. So easily we can find the confidence interval. 100, 1 minus alpha percentage confidence interval. Okay. And also answer for the data. Very easy. Okay. Just one more thing. Actually, on the way we try to the multiple comparison using t-test. We have so many information because we observe that yi bar means that the sample average always follow normal distribution with the mean is mu I and the variance is sigma square over n. Hence, we can know the information about mu I. Okay. If in the question we're not asking for the differences between mu I and mu j, If we only focus on mu A, we also able to answer for the question about the t-test, about the confidence interval for the single parameter mu A. You should able to do it. Okay, it's just the same question as t-test, but using sigma square. Replace sigma square by sigma hat square. Sigma hat square is MSE. Okay, it's return to the knowledge of chapter 4 and chapter 5. Okay, that's the reason why I told you that chapter 7 is some kind of extension of chapter 4, chapter 5, chapter 6. Okay, is this clear? Any question? Okay, exercise. Still be question about example 1. We just done together that there exist the differences between the means, between the tensile strength means of different levels of Howard's concentration. Now we continue to use the multiple comparison LSD method to know which pair of the means will be different to each other. Okay, let's do it together. Maybe actually I should start with the new page. Okay, anyway.